Welcome to our practice session. So you guys took that earlier this morning. Now we're going to go over the answers. So we'll start in the short answer section. The first question asks you about the chicken game. So that's where you have two players, they drive their cars toward each other. The chicken is the one who swerves, and the brave one is the one who does not swerve. So in order to avoid a collision, one player has to swerve, and the one who swerves first is the coward or the chicken. So let's say there are two types, normal and tough, and you're going to assume your opponent is a normal person. So what you're trying to do here is try to convince your opponent that you're going to be a tough guy who's never going to swerve no matter what. So in order to do that, you're going to get some tattoos and a wild haircut. Is that an example of signaling or screening? Explain. So this would be an example of signaling. And the idea is that with signaling, that's when the more informed side takes action to reveal what they are. So signaling and screening both came up in the context of asymmetric information, where one player has information that the other player does not have. So you know what kind of type you are, but your opponent does not. So you have more information about what you are truly like. So on the other hand, just for some bonus review for you guys, screening was the other kind. That's when the less informed side, in this case your opponent, would try to screen you, I should say, to try to test you in some way in order to extract information. But in this example, where you're getting some tattoos and a haircut, that is not taking place. So number one's about signaling. All right, moving on. So that's short answer number 2. That one says explain the opponent's indifference property. That comes up when we're looking at mixed strategies, where both players are, or at least one player rather, is randomizing. So you have to make your opponent indifferent between each of their pure strategies. And why is that true? Well, consider what would happen if they weren't indifferent. If you're not indifferent, if one strategy is just better in expected value, you're always going to play the better strategy. So you have to have equal expected values for each of your opponent's pure strategies. So we use that approach to find what's the mixed strategy Nash equilibrium in 2x2 games. We couldn't use it so much for 2x3 or 3x3 games because oftentimes there players don't use all their strategies, so this wouldn't work so well in that case. All right, that wraps up number 2. Moving on to number 3 coming up next. Let me get some more paper. Number 3 asks about the Nash equilibria and problem number 1, not subgame perfect, so we gotta solve problem number 1 first. So let's do that. So problem number 1 is based on the ultimatum game. We played this in class quite a while ago. So, quick refresher, there are 2 players, a proposer and a decider. The proposer could suggest how to split the $10. So I could say, I get 9, you get 1, or you get 5, I get 5. There are actually more options in the original game, but we just try to strip it down here and make it just 2 options to ease the analysis. The decider could either accept or reject, so I'm using A for accept and R for reject. If the decider accepts, then that's what happens. So if proposer says 9, 1 and decider accepts, then proposer gets 9, decider gets 1. The interesting part of this game is that if the decider rejects, then actually both sides get nothing. So to see if a Nash equilibrium are not subgame perfect, we first have to find which Nash equilibria are subgame perfect. Says find the rollback equilibrium. Remember, rollback and subgame perfect Nash equilibria were the same thing. So the decider is here, and the paths are proposer on top and decider on the bottom. It was color-coded in the version you saw, but my printer is out of color ink, so I'm using black and white. So the decider's paths from the bottom. If the decider is down here at this node, they'd rather accept and get a path of 1 rather than reject and get 0. If they're over here, they would rather accept and get 5 than reject and get 0. Oops. There should only be an arrow on the accept branch. Having established that, the proposer can then decide if they want to go 9-1 or 5-5. The proposer picks 5-5, they're going to get just 5. Our proposer's on top here. If they offer 9-1, they're going to get 9. So proposer would rather offer 9-1. So our subgame perfect Nash equilibrium, or the rollback equilibrium, is going to be 9-1 and accept 9, also accept 5. Remember, a strategy specifies what you do at every one of your information sets. So even though this one over here doesn't happen in equilibrium, we still specify what the decider would do if, by chance, we somehow got there. So I still have to include A5 in my Nash equilibrium. All right, so are any of the Nash equilibrium problem 1 not subgame perfect? So we know which ones are subgame perfect. Now you got to find all the other Nash equilibria. So to do that, we have to rewrite the game in normal form, also called strategic form. So we're going to make the proposer the column player and decider the row player. Proposer has 2 strategies. (9-1) and 5-5. Our decider here is going to have 4 strategies. So I could play accept 9, accept 5. They could reject both of them. Accept the 9 but reject the 5. And reject the 9, accept the 5. So that's going to tell us how many rows and columns are going to be in our game table. So let's fill in our payoffs. So if they always reject, that's going to mean 0, 0 all the time. Let's see, if the proposer offers 9, 1, and that gets accepted, it can also be 1, 9. Remember, row players' payoffs always come first. Here, the decider is the row player, so they're getting 1. That's 1, 9, not the other way around. And here they're accepting the 5, 5 offer, so both of them get 5. In this row here, in the cell, proposer is offering 9, 1, and decider is playing accept, so that's going to be 1, 9. Here, proposer is suggesting a 5, 5 split, and rather oddly, decider is rejecting it. Not a strategy I would recommend. Here, decider is rejecting 9, 1, but accepting 5, 5. All right, so now we have our table. Let's use our best response analysis to identify all the Nash equilibria. If a proposer plays 9, 1, then best responses are these ones, getting a payoff of 1. If the proposer suggests a 5, 5 split, decider's best responses are these ones, getting a payoff of 5. If the decider is playing accept, accept, proposer's best response is 9, 1. If decider is playing accept 9, reject 5, best response is to offer 9, 1. And here, decider is rejecting 9, 9, but accepting 5, 5. So best response is to offer 5, 5. And here, they're both best responses. You get 0 either way, so it doesn't matter. So what have we got here? We have a total of 3 Nash equilibria. So they are accept 9, accept 5, and 9, 1. Accept 9, reject 5, 9, 1. And also reject 9, accept 5, 5, 5. So the original question asked us, which of these are not subgame perfect, which ones and why? So we established this one over here is subgame perfect. So these two must be not subgame perfect. So we gotta explain what is not subgame perfect about these two Nash equilibria. So for this first one here, the decider is rejecting 5-5. But we know that if the decider actually were at this node, they would rather accept 5-5. It's better to get 5 than to get 0. So that is a violation of subgame perfection. So that is how we address that Nash equilibrium. I almost said ruled out, but ruled out is not quite the right word. It still is a valid Nash equilibrium, but it's arguably not terribly realistic because of this non-subgame perfect issue. This last one here also has a problem. So here, the decider is saying they're going to reject a 9-1 offer, and based on that non-credible threat, the proposer is spooked into offering a 5-1 rather than the 9-1. So it's also not subgame perfect because the issue there is that if we really were at this node where the proposer has made that 9-1 offer and we're at this subgame, best response to the decider is to play accept and get 1 rather than reject and get 0. So that's a non-credible threat. The decider is saying, I'm going to reject 9-1, so you better offer 5-5, but that threat should not be believed. So that wraps up short answer number 3. We found all the Nash equilibria and we identified which ones are not subgame perfect. So moving on, we'll look at the problem section. So look at the same game. We got finding the, we actually did this already, so I guess I'm doing things a bit out of order here for the practice session. That's a bit inconvenient. For the exam, it will not be ordered like that. So there are no exam questions that reference a different part of the test. So the short answer part of the exam is all self-contained. It's not going to reference the problem section. I guess I have just a rather awkward arrangement here with our practice session. All right, so we did number 1. Let's look at number 2 in the problem section. So this is the, I posted a link to this up on my courses. You'll find it very entertaining, this game show where the two options are split or steal. And if you both play split, you get 5-5. If you steal and your opponent splits, you get the whole pot, whole $10, or I think it's actually a lot more than $10 in the game. But if you both play steal, then you both get 0. It's not quite a prisoner's dilemma game, but it's a very similar spirit to the prisoner's dilemma, that the cooperative outcome is not a Nash equilibrium. So to be a prisoner's dilemma, the cooperative outcome has to be strictly dominated, but here it's not actually strictly dominated. So our first part here is find a pure strategy Nash equilibria, assuming the game is played only once. So if our opponent is going to play split, our best response is to play steal and get 10 rather than just 5. If our opponent plays steal, doesn't matter, we get 0 either way. If we're playing split, opponent's best response is to play steal and get 10. If we play steal, opponent gets 0 either way, so they're both best responses. So you can see it's not really a prisoner's dilemma game. There are actually 3 Nash equilibria here, not just one like in the prisoner's dilemma. So I'll just write them out. I'm out of space. Let's go down here. All right, so we did part A. Now in part B, we say, now suppose the game will be played infinitely many times and your opponent makes the following speech. I'm going to play split. If you also play split, then I'll play split again in the next round, and that's going to continue as long as we keep cooperating. But if you're a defect and play steal, then they're going to punish us by playing steal forever. So here are our choices. We could cooperate by playing split forever, or we could defect by playing steal in the first round. Then they punish us and play steal forever. So you'll look at what's our payoff going to be in each case. So if we cooperate, we both play split in round 1. Then next period, we both split again. Because it's in the future, we got to discount it by delta. Next round, we still keep cooperating, so we split again. We get 5. And now, that's 2 periods from now, so we discount it twice, delta squared. Then 5 delta cubed, and so on. So what does that come out to? Well, all these terms have 5 in common, so we can factor out the 5. It's delta plus delta squared, delta cubed, etc. Then we gotta use our trick that we had earlier in chapter 10. We said that if absolute value of delta is less than 1, then this comes out to 5 times 1 over 1 minus delta. And we're told what delta is here. We said delta is 0.7. So that comes out to 5 over 1 minus 0.7, which is 5 over 0.3, which will come out to 50 over 3. So that's what we get if we cooperate. Now, we got to compare it to what do we get if we defect. So if we exploit them and play steal, when they're playing split, we get a big payoff in round 1. The problem is they then punish us and play steal forever. So first time we get 10 because we played steal and they played split. In the next round, they're playing steal to punish us, and we also play steal, so we're both getting 0 there. So in the future, say discount by delta. Next round, we get 0 again because we're being punished with both playing steal. So I guess multiplied by a delta squared, 0 delta cubed, but it really doesn't matter. They all just cancel out because there's 0 in front of it, so that's going to yield just 10. All right, so if we defect, we get 10. If we cooperate, we get 50 over 3. 50 over 3 is going to be 16 2/3, is that right? Yeah, 16 2/3. So it's better to cooperate. So that wraps up problem number 2. We have one last problem. That's the third one. This is adapted from your textbook. I simplified a little bit. Sometimes your book problems get really long. I think the book takes 3 paragraphs to tell a story, but you really just summarize it in 1 paragraph. So let's work with this version. So you have 2 kinds of professors, and the university wants to only tenure the brilliant ones. Now, if you're brilliant, it's easy to get papers published. That is, if you're merely good. So as you can see, the payoff for the one who's good is going to be lower for the same number of papers because it's just harder for them. And we want to have, they both get an outside option. They could get a payoff of 50 by doing some other kind of job. So you just set things up so that only the brilliant professors want to work for a university and the good ones do not. So use some value of n such that the payoff for working for the university for the brilliant is better than the outside option, and the payoff for the ones who are merely good is going to be worse than the outside option. I should say more precisely, greater than or equal to. Outside option is 50. So this is true. The brilliant professors prefer to work for our school. If the second condition is true, then the ones who are good are not going to work for us. They'd rather get that outside payoff of 50 from some other job. So what is that going to imply? We subtract 50 from both sides and we get 150, and I put the 3n over there, it has to be greater than or equal to 3n. With the 50 over there, you have 150, and this has to be smaller than or equal to 6n. I am running out of space. Let's move down. Let's move over here. So they have 150 being greater than or equal to 3n, and 150 also being less than or equal to 6n. So for this one over here, divide both sides by 3. You have to have 50 being greater than or equal to n. If we move this one over here, divide both sides by 6, then we're going to get, so 150 over 3 is going to be 50. So then we divide that by 2, it's going to be 25. So what that tells us, we need n to be between 50 and 25. So that wraps up problem number 3, and that's all we have for our practice session. So stay healthy out there, and best of luck on the exam.